Welcome back to Calculus 3. I'm Dr. Jeff Groh. We're going to begin today's lecture by talking about centers of mass, and centroids. We'll begin this discussion by talking about discrete masses distributed linearly with a fulcrum point. We'll have mass 1, mass 2, and so on at position 1. These positions will be from the left-hand endpoint of this bar, x2, and so on. Also, let's suppose that the fulcrum point is positioned so that we get perfect balance. It's at the point x bar, the center of mass. Now, let's think about this center of mass. Mass 1 has a lever arm length. The lever arm length is going to be x bar minus x1, and the mass applied at that point gives us a moment of mass 1 times x bar minus x1. That's the moment of this mass about the center of mass. Also, for x2, we have a moment, m2 times x bar minus x2. And we keep adding these all the way up until we get to the last mass, which we'll suppose is the nth mass. The moments on the masses on the right should exactly counter the moments of the masses on the left, in which case we should get a total of 0. That's when x bar is placed perfectly so that we get balance. Now, that means 0 is the sum, as k goes from 1 to n, of m sub k times x bar minus x sub k. Distributing, we have 0 equals x bar can be factored out of the first sum. The sum as k goes from 1 to n of m sub k, minus the sum as k goes from 1 to n of m sub k times x sub k. We'll position these so that we have positives on each side of the equation, and we'll solve for x bar, the center of mass. We find x bar is the sum as k goes from 1 to n of mk xk divided by the sum as k goes from 1 to n of mk. Adding up the total masses across the balance beam gives us the total mass. Adding up the mass times the length to the left endpoint of the balance beam gives you the total moment about the origin of this balance beam. So the center of mass is the total moment divided by the total mass. We can generalize this by allowing a continuous distribution of mass across the balance beam. In this case, we'll have a density. Density is normally denoted by the lowercase Greek letter rho. This is so commonly known. When I solve a crossword puzzle and the clue is symbol for density, the answer is RHO, rho. So this is common knowledge throughout all of society. Density is denoted by rho. In this case, we have a linear density. A linear density will have units of mass per length. So kilograms per meter, for instance. Generally, for mass densities in a volume, it will be kilograms per cubic meter. But in this special case of a linear density, it's mass per unit length, kilograms per meter. In this particular instance, density is a function of position x along the balance beam. At some place x, we'll take a very thin slice of width dx. The total mass on that little slice is dm, the element of mass. It's the density times the length. Density has units of kilograms per meter. If I multiply an element of meters, I get kilograms, an element of mass. To get the total mass, which I'll denote by m, you integrate rho of x dx. You add up these little elements of mass from the beginning point to the end point. To get the center of mass, I need the total moment divided by the total mass. The elements of moment are the elements of mass times the lever arm length from the left-hand endpoint. If we add those up from A to B, we get the center of mass. For finding the center of mass of a region in the plane with a density rho of x now based upon position, you carve out a little element with area dA at some point x. We'll have two lever arms. The lever arm about the x-axis, which is y, and the lever arm about the y-axis, which is x. So we'll have two different moments in this case. The total mass is still the integral of density times the element of area over the region R. In this case, the integral will be a double integral because you're integrating against an element of area. Remember, in plane regions, density will have units of kilograms per square meter. The element of area will have units of square meters. When you multiply those two together, you get units of mass, kilograms. If you add that up over the region R, you get the total mass. To find the center of mass, we need to find the moment about the y-axis, which we will denote by m with a subscript of y. To find that, we take the lever arm, x, and multiply by the element of mass. Mass times lever arm length. If we add that up over the region, we get the moment about the y-axis. The x-coordinate of the center of mass will be the moment about the y-axis divided by the total mass. The moment about the x-axis will be the sum over the region R of the y-coordinate, rho of x dA, and the center of mass will be x bar y bar, where x bar is the moment about the y-axis over the total mass, and y bar is the moment about the x-axis divided by the total mass. For a centroid, we assume that the density is constant. You may as well assume that the density is identically 1. That will simplify the formulas. Let's do a quick example. Let's suppose that we're dealing with the region bounded by y equals x minus 1, y equals minus x plus 1, and x equals 0. Let's calculate the centroid. First, we'll find the total mass. Remember, the total mass is the integral of the region, R, of density times the element of area. Since we're looking for a centroid, density in this case will be identically 1. And if we just integrate the area element over the region, we get the area of the region. In this case, we really have very little to calculate. What we have here is a triangle. The area of a triangle is pretty easy to find, and this one particularly easy because you can cut it in half and rotate the bottom half to create a square, 1 on each side. The area is 1. To find the moment about the x-axis, you integrate on the region y times rho dA. Again, rho is identically equal to 1. So you're adding up y values across this region. If you add up y's across a region with positive y's and balancing negative y's, you must get 0. If you have an odd function of y, and you're integrating over a region that is symmetric through the x-axis, you have counterbalancing positive y's and negative y's, and hence the double integral will equal 0. Let's check this. The moment about the x-axis is the integral on the region of the y's times dA. In this case, we can set up the double integral using vertical cross sections. So at each x, we go from lower curve to upper curve, from x minus 1 to minus x plus 1. And the x's go from 0 to 1. Integrating with respect to y, we get the integral from 0 to 1, y squared over 2, evaluated from x minus 1 to, notice that the upper limit of integration is the minus of the quantity x minus 1. If you plug in a quantity with a negative and square it, the negative goes away. If we subtract the same quantity without the negative, you get 0. Now, let's check the moment about the y-axis. That should be the integral over the region of x dA, since the density is identically equal to 1. In our region, all of the x's are positive, which means we must get a positive value here. We'll set up the limits of integration over the region just as before. Integrating with respect to y, we get x times y, evaluated from x minus 1 to the negative of x minus 1 dx. We have then the integral from 0 to 1 of x times negative x minus 1 minus x times the quantity x minus 1. We get 2 of the same thing, so I'll just put a 2 right here and cross out the second term. We'll distribute to get a positive 2x and then a minus 2x squared. Integrating, we have x squared minus 2x cubed over 3. And evaluating, we have 1 minus 2/3, which is 1/3. The centroid then, which represents the geometric center of the region, you'll recall that was my divided by m, comma, mx divided by m. My is going to be 1/3 and m was 1. Mx is 0. You might have deduced just on the symmetry of the region that y bar would be equal to 0. The balance point must lie on the x-axis. And what is more, it should be closer to 0 than it is to 1, because most of the region is over here closer to the y-axis than it is to the point x equals 1. For students in my classes, I like to illustrate this last example with a sheet of paper. we will also need a measuring tape. Now we need to start by making an equilateral triangle. So I'll fold this paper along diagonal. And we'll have a little extra tab here that we need to eliminate. We'll need to fold to eliminate that little extra tab. You may need to fold back and forth a couple times to tear this properly, but we should be able to tear it right along the tab. Now, we'll do the same thing with this other piece. We have ourselves a nice equilateral triangle right here. I need to find the center line. To find the center line, what I'll do is I'll fold this in half. And that will give me a nice location of that center line. I want to measure 1/3 of the distance from the larger side. I'll mark that right on the center line, right here. Then, that should be the centroid. And I should be able to tell, because I should be able to balance my pin right on that point. As you can see, the mathematics that we're deriving here is not something purely abstract, but something that you can visualize in your world. I like to then pass that object around to my students in my classroom so they can see for themselves. So, since I can't do that here, you should make one yourself. Let's do another example. Let's find the centroid, where my region now is going to be semicircular, some radius, I don't know, let's say 1. So my curve is given by y equals the square root of 1 minus x squared, solved for y in the formula x squared plus y squared equals 1. My region R should have an x-coordinate of the centroid equal to 0. Let's see. To find out, let's calculate my, the moment about the y-axis. That should be the integral of x times rho, which is 1, times the element of area. Clearly, if you're adding up x's throughout this region, you must get 0. That tells us then that x bar, which is my divided by m, must be 0. We need to calculate y bar next. Y bar is mx divided by m, where m is the total mass. And when you're calculating total mass for a centroid, you're calculating the integral of rho dA, but rho is 1. And so that just gives you the area of the region. The area of this region can be calculated without doing a double integral. Instead, we just take half the area of the disk, or pi over 2. To calculate mx, we need to add up over the region y times rho times dA, rho being 1. We're just adding up the y values. This should be a positive number. Now, this region is easiest to parameterize in polar coordinates. So we're going to have to convert everything to polar. Y in particular must be converted to polar. And in particular, that's r sine theta. The element of area in polar coordinates is r dr d theta. Don't forget that r. Theta will go from 0 to pi, 0 to pi, and r will go from 0 to 1. Because all of the limits of integration are constant, we can integrate with respect to theta first. If we integrate the sine function from 0 to pi, we get the area of one bump, and one bump gives you 2. All that's left is r squared dr. So we get 2 r cubed over 3 evaluated from 0 to 1, and that gives us 2/3. The y-coordinate of the centroid is then 2/3 divided by pi over 2, or 4 over 3 pi. If pi is approximately 3, this is about 4/9, or about 0.44. As you can see, that's a little bit less than half of the distance up from the origin, but it's a little bit more than the 1/3 in the equilateral triangle example. You kind of expect that because if you have more of the region above that dividing line at 1/2, the centroid should be lifted upwards away from the origin. To find centers of mass in R3, we'll have some generic kidney-shaped region in R3. In this case, you carve out little volumes, dv at x, and what you do is the total mass is the integral over the region R of the density times the element of volume. In 3 dimensions, density has units of kilograms per cubic meter, and the volume element has units of cubic meters. So when you multiply the two, you get units of kilograms. When you add that up over the whole region, you get the total number of kilograms in the region. You get the total mass. There are going to be 3 moments. Each of these will have a z coordinate, a y coordinate, and an x coordinate. So you're going to have moments about various planes. The z lever arm is the moment about the xy plane. So to calculate the moment about the xy plane, you add up z times rho times dv. Lever arm times element of mass added up over the region gives you the total moment about the xy plane. To get the moment about the xz plane, you of course integrate y. The total moment about the yz plane, you add up x rho dv across the entire region. Now, what is the center of mass? The x-coordinate of the center of mass is the moment about the yz plane divided by the total mass. Remember, myz is the moment about the yz plane. It has a lever arm of x. The y-coordinate of the center of mass is mxz divided by m, and the z-coordinate will be mxy divided by m. Let's do a quick example. Let's suppose that we have a hemisphere, a solid hemisphere. Let's also suppose that the density is 2 minus the radius of points from the origin within the hemisphere. We have a bit of a notational problem in describing this equation. In spherical coordinates, density is rho and the radius is also rho. So we need to make a distinction between these two different values of rho. So let's say the density is rho tilde. That way we can use the usual notation for the radial variable in spherical coordinates, rho. Now, the total mass will be the integral over the region of our density times the volume element. Notice that the density will get less as we go out from the origin. The density will decrease. We'll have 2 minus rho. The volume element is rho squared sine phi d rho d phi d theta. Theta, to sweep out this entire region, will go from 0 to 2 pi. Phi will go from straight up, remember it's the colatitudinal angle, but it's from straight up to straight to the side in each direction. So it goes from 0 to pi over 2. And the radius goes from 0 to 1. Notice that all of the limits of integration are constant. By Fubini's theorem, we can integrate with respect to any variable we want. In this case, there are no thetas inside the first two integrals, either in the limits of integration or in the integrand. So we get 2 pi for free. We may also integrate with respect to phi next. The only phi that appears is in the sine of phi, and we're integrating that sine phi from 0 to pi over 2. Half a bump. Half a bump gives you 1. The only thing left is to integrate from 0 to 1, 2 rho squared minus rho cubed d rho. This gives us 2 pi times 2 rho cubed over 3 minus rho to the 4th over 4, evaluated from 0 to 1. We have then 2 pi times 2/3 minus 1/4. That gives us 8 minus 3 is 5/12, times 2 is 10 pi over 12, or 5 pi over 3. That is the total mass. I'll write that over here for safekeeping. Let's calculate MYZ, which is the integral over the region of x times the density times the volume element. Setting this up as a triple integral, we have to remember that x is rho cosine theta sine phi. I want you to memorize those formulas, the transformation between rectangular coordinates and spherical coordinates. Spherical coordinates are definitely indicated on a region having this symmetry. So the formulas were x equals rho cosine theta sine phi, y equals rho sine theta sine phi, and z equals rho cosine phi. We're multiplying by the density, which is 2 minus rho, and then the volume element is rho squared sine phi d rho d phi d theta. To integrate over this region, theta needs to go from 0 to 2 pi. The colatitudinal angle phi needs to go from 0 to pi over 2 in all directions, and the radius goes from 0 to 1. Now, why is this obviously 0? Due to Fubini's theorem, since all of the limits of integration are constant, we can integrate with respect to whichever variable we want. Let's integrate with respect to theta first. The only thetas that appear in the integrand are in this cosine theta, and we're integrating that from 0 to 2 pi. If you integrate cosine from 0 to 2 pi, you have to get 0. Similarly, mxz is equal to 0, where in this case you're integrating y. y was rho sine theta sine phi. And if you integrate sine from 0 to 2 pi, you also get 0. The only moment that isn't obviously equal to 0 is mxy, where you're adding up over the region z times rho bv. All of the z's are non-negative in this case, so you'd better get a positive result. Z is rho cosine phi. Our density is 2 minus rho, and the volume element is rho squared sine phi d rho d phi d theta. We're still integrating as theta goes from 0 to 2 pi, and as phi goes from 0 to pi over 2. The radius goes from 0 to 1. In this case, you have a cosine phi times sine phi. But there are absolutely no thetas, so we will get a 2 pi for free. Sine phi times cosine phi, you recall, is 1/2 sine of phi over 2. But we're still multiplying by this rho cubed times 2 minus rho. I'll write that as 2 rho cubed minus rho to the 4th d rho d phi. Let's integrate with respect to phi next. Integrating sine, you get a negative cosine. But don't forget that when you integrate sine phi over 2, you have to divide by 1/2. We'll still have the 2 rho cubed minus rho to the 4th d rho. Plugging in the pi over 2, we'll have minus the cosine of pi over 4. That's minus the square root of 2 over 2. But then we have to subtract what we get when we plug in 0. When we plug in 0, we get negative 1. Still have 2 rho cubed minus rho to the 4th d rho. So we have this constant coming out. It's going to be 1 minus root 2 over 2, and then we'll integrate. We'll have 2 rho to the 4th over 4 minus rho to the 5th over 5, evaluated from 0 to 1. Distributing the 2, we'll have pi times 2 minus the square root of 2, and plugging in, we'll have 1/2 minus 1/5. 1/2 minus 1/5 is 5 minus 2 is 3/10. So we'll have 3 pi over 10 times 2 minus the square root of 2. That is the moment about the xy plane. To get the z coordinate of the center of mass, we take this moment and divide by the total mass. We have z bar is mxy over m. That's going to be 3 pi over 10 times 2 minus the square root of 2 divided by 5 pi over 3. The pi's will cancel. We'll have to invert and multiply that fraction. We'll have 9/50ths times 2 minus the square root of 2. Also, x bar and y bar are both 0. In our next example, we're going to assume that the density is e to the minus x squared plus y squared plus z squared to the 3/2. You can see that this is the spherical coordinate rho squared. Rho squared equals x squared plus y squared plus z squared. So in fact, we have negative rho cubed in the exponent of the exponential function. So in fact, we have negative rho cubed in the exponent of the exponential function, expressing the density in spherical coordinates. Let's suppose that we're dealing with a sphere. And let's give the radius equal to 1. Let's just find the total mass. The total mass is going to be the integral over our region where theta will go from 0 to 2 pi, phi will go from 0 to pi, and rho will go from 0 to 1. We have e to the minus rho cubed as our density. The volume element is rho squared sine phi d rho d phi d theta. By Fubini's theorem, we can integrate with respect to whichever variable we want. Let's integrate with respect to theta first, since there are no thetas on the limits of integration or in the integrand of the other two inner integrals. That gives us 2 pi for free. If we integrate with respect to phi next, the only phi that appears is in the sine phi. And if we integrate sine over half a period from 0 to pi, we get 1 bump. And 1 bump gives you 2. We're left with the integral from 0 to 1 of rho squared e to the minus rho cubed d rho. This looks like a job for a u substitution. U equals minus rho cubed, so that du is minus 3 rho squared d rho. We don't have the minus 3, so we'll divide that off. We'll encapsulate this as a little side computation. Out front we have this 4 pi. We're going to hit that with a negative 3. We'll have negative 4 pi over 3. We'll now transform the limits of integration. If rho is 0, then u is 0. And if rho is 1, then u is minus 1. We'll have e to the u du. Integrating, we can switch the limits of integration. That will cancel out the negative in the front. That'll give us a positive 4 pi over 3 e to the u evaluated from minus 1 to 0. Plugging in the 0 gives 1. Plugging in minus 1 gives e to the minus 1. The number e is about 2.71828. Now, the reciprocal of that then will be 1 over 2.71828. We'll have a positive number here. The moments that we've dealt with so far are sometimes called first moments. We're now going to talk about second moments, or moments of inertia. The moment of inertia about the x-axis for regions in the plane are going to be the sum over r of y squared rho dA. And the y moment of inertia is then obviously the sum over r of x squared rho dA. There is also something called the polar moment. It's denoted by I naught and is the sum over r of r squared rho dA, where r is the polar coordinate r. This will be because r squared is x squared plus y squared equal to the other two moments added together. This is basically all I want to say about moments of inertia. You're going to study this in physics. I'll let them cover this in more detail. We're now going to talk about change of variables. In multiple integration. And in particular about Jacobians. The changes of variable that we have seen so far, like the change between polar and rectangular in the plane, Let's suppose that x is a function of variables u and v, and y is a function of variables u and v. This is in direct analogy to the situation between rectangular coordinates and polar coordinates. In the uv plane, we might have some rectangle of width du and dv. Our transformation function, let's call this f of uv equals xy, will distort the region to something more bent. So how do you translate the relationship between the area that's been distorted to the area that is not distorted? Set xy to be a function phi of uv, and it's given by x of uv, y of uv. Remember, in the uv space, we're dealing with some nice little rectangular region. The function phi will transform that in the xy plane to some bent region. We can hold v fixed. If we allow x to vary, holding v fixed, we'll go along one of these curves over here in the range space. If we take the derivative with respect to u, we end up with a tangent vector, tu. Similarly, tv will be the tangent vector that we get by holding u constant and allowing v to vary. That'll be the derivative of phi with respect to v. While we might have a right angle in the domain, here in the range you do not necessarily have a right angle. What is more, you can estimate the area of the bent region by, especially if this is really small, du and dv in width, some infinitesimal distance, the area element in the bent plane is going to be estimated by the following. It's the norm of tu times du cross tv times dv. Remember, when you calculate the norm of the cross product of two vectors, you end up with the area of the parallelogram spanned by the two. We're multiplying these vectors by infinitesimals. We're looking at a very small rectangle in the range space here. We can factor the du and the dv out, both of the cross product and the norm, and we'll be left with the norm of tu cross tv, du dv. Du times dv is the area element in the domain space. The area element in the range space is related to it by this formula. Let's look at this cross product and the norm in a little more detail. Tu, we said, was d phi du, and that's going to be dx du, dy du. Tv then is dx dv, dy dv. To calculate the cross product, we kind of have to expand these to include another coordinate equal to 0, in which case tu cross tv will have coordinates equal to 0, 0, and then the last coordinate will be the minor involving these first two coordinates. That's going to be dx du, dx dv, dy du, dy dv in a determinant. To calculate the norm of tu cross tv, we square the coordinates, add them up, and take a square root. But remember, the square root of x squared is equal to what? The absolute value of x, not x. So we get the absolute value of the determinant of the matrix of partial derivatives. We're going to make a definition. The Jacobian of the transformation xy equals x of uv, y of uv is denoted by, now I have to be honest, there's more than one notation here, and both of the following notations are in common usage. One common notation for the Jacobian is J. This doesn't give a lot of information about what's going on or how we're going to use it. So we will usually use this notation for the Jacobian. Another common notation is the following: dx comma y over du comma v. We will typically use this notation. Dx comma y over du comma v is the absolute value of the determinant of the matrix of partial derivatives. Now, due to the last computation, we have the following theorem. Provided, of course, the coordinate transformation is suitably smooth, we have the following. dx dy, the element of area in the xy space, is related to the element of area in the uv space by the Jacobian times du dv. Also, if you have some domain in the uv space and your coordinate transformation transforms that to some region r in xy space, then the integral on r of some function of x and y dx dy will be equal to the integral over the domain D f of x of uv y of uv. The price you pay for going to uv space is the Jacobian. Du dv. A natural example is x equals r cosine theta, y equals r sine theta. The Jacobian is the absolute value of the determinant of the matrix of partial derivatives. First, let's take the derivative of x with respect to r, and then we'll take the derivative of x with respect to theta. We'll take the derivative of y with respect to r, and then with respect to theta. We'll have r cosine squared theta minus negative r sine squared theta, which adds up to r. We deduce then that dx dy is the Jacobian times dr d theta, and we've just seen that the Jacobian is r, so we get r dr d theta. Go figure. In our next example, Let's suppose that we're integrating over a parallelogram, having vertices 0, 0, 0, 1, 2, 4, and 2, 5. So I've shaded the region R that we are going to integrate over. And let's suppose that we're integrating over R square root of 2x times y minus 2x. How do we set this up? Well, it seems a little complicated, and we might take advantage of certain simplifications. Look at this line. This line goes over to up 4. It has a slope of 2 and it goes through the origin. It is y equals 2x. And the top line is y equals 2x plus 1 because we have an intercept of 1. This means that the quantity y minus 2x in this region goes between 0 and 1. This suggests that we make the following substitution. Let's set u equal to y minus 2x. In that case, u will go between 0 and 1. Let's also set v equal to 2x. In this case, since x goes from 0 to 2, v will go from 0 to 4. We can transform to an integral where we have variable limits of integration because we go from bottom curve to top curve, to one where all of the limits of integration are constant. The price that we pay is a Jacobian. So far, we've defined these coordinate transformations, x equals y minus 2x, which we now know is v. That gives us y equals u plus v. X is 1/2 v. This will give us our coordinate transformation. To find the Jacobian, we need the absolute value of the determinant of the matrix of partial derivatives. The derivative of x with respect to u is 0. The derivative of x with respect to v is 1/2. The derivative of y with respect to u is 1. And the derivative of y with respect to v is 1. The determinant is 0 minus 1/2. Taking the absolute value, we get 1/2. How does the integral transform then? We'll have the square root of v was 2x, and u was y minus 2x. The element of area dx dy is going to be the Jacobian 1/2 times du dv. V ran from 0 to 4, and u ran from 0 to 1. This integral will be a lot easier to evaluate. We'll move the 1/2 out and integrate with respect to u first, holding v constant. We'll have v to the 1/2, u to the 1/2. Integrating u to the 1/2, we'll have u to the 3/2 times 2/3, evaluated from 0 to 1. Evaluating, we'll have 1/3, the integral from 0 to 4, of v to the 1/2 dv. That's 1/3, v to the 3/2 times 2/3, evaluated from 0 to 4. Remember that when we are evaluating something to the power of 3/2, we get a root a. So here we have 2/9. 4 root 4 is 8 minus 0. So the value of the integral is 16/9. The original integral would have been the integral from 0 to 2, the integral from 2x to 2x minus 1, the square root of 2x times y minus 2x dy dx. I think the way that we evaluated it was a lot easier. I want to evaluate the integral of y squared over the region R, where R is the region bounded by the curves x equals y squared. That we're going to work in quadrant 1 here. This is a parabola on its side. X equals y squared minus 4. This is a parabola that goes from minus 4 and does not intersect the other parabola. X equals 9 minus y squared. Putting a negative on the y squared makes the parabola open the other way. And then x equals 16 minus y squared. Now, the region that we're going to integrate over R is this weird little bent region. This is not a nice parallelogram. The sides are curved. All of the sides are curved. An attempt to use vertical cross sections will require 3 double integrals, and the same is true for horizontal cross sections. There has to be a nice way to integrate this by converting to a good coordinate system. Let's try the following. Note that on these first 2 curves, x minus y squared equals 0 and x minus y squared equals minus 4. Suppose we define a new variable, u equals x minus y squared. Then u will go from negative 4 to 0. We can take the same ploy with the other 2 equations. Here we have x plus y squared goes from 9 to x plus y squared equals 16. In this case, if we set v equal to x plus y squared, then v will range from 9 to 16. Let's summarize what we have here. We have a new variable u, which is x minus y squared, and it takes values in the interval negative 4 to 0. We have a new variable v, which is x plus y squared, and it takes values between 9 and 16. The Jacobian formula that we derived requires x as a function of u and v, and y as a function of u and v. But I want you to notice something. We're going to calculate the Jacobian 2 different ways. First, we're going to calculate the Jacobian of uv with respect to xy. This will be the absolute value of the matrix of partial derivatives. The partial derivatives of u with respect to x and then y will be 1 and negative 2y. The partial derivatives of v with respect to x and then y will be 1 and then positive 2y. We'll get 2y minus negative 2y, and that is 4y. Now, to get the Jacobian in the other way, we have to solve for x and y. Notice that if we add the 2 equations, we'll get 2x is u plus v, or x is u plus v over 2. To solve for y, we can calculate v minus u, the x's will cancel, and we'll end up with 2y squared. We'll divide the 2 off. That gives us y squared. To get y, we'll take the square root. You can see the Jacobian calculated with respect to this coordinate transformation will be a bit more complicated. Let me store what we have so far over here. we have the absolute value of the determinant of the matrix of partial derivatives. The partial derivatives of x with respect to u and v are 1/2 and 1/2. The partial derivatives of y with respect to u and v are a little more complicated. We have this 1/√2 times the quantity v minus u to the 1/2. Calculating the derivative with respect to u, we'll have to use the chain rule, and that'll give us a minus. But the derivative of a square root is 1/2 root. 1/√2 is coming for the ride. 1/2 root v minus u times the derivative of the inside, which is minus 1. The only difference between that and the derivative with respect to v is that we don't get the minus 1. We'll have the Jacobian of xy with respect to uv is equal to 1/4√2 square root of v minus u, and then minus and minus the same thing. So we end up with twice that quantity. Keep in mind, y squared is v minus u over 2. We put the 2 over here and take a square root. We'll have a 2 canceling. We'll have 1/2√2, and the square root of v minus u is √2 times y, which is 1/4y. Go back over here. The Jacobian the other way around was 4y. This Jacobian is 1/4y. I think you can see there must be a theorem going on here. The theorem is that the Jacobian uv with respect to xy will be 1/, the Jacobian of xy with respect to uv. Our integral then, our element of area is dx dy. We want to transform that using our Jacobian. So we're going to integrate over the domain of parameters for u and v, y squared, our Jacobian, du dv. So we can transform to the other variables. We have the integral over the domain for u and v's, but I'm going to simplify this before transforming. Remember, this Jacobian was 1/4y. We can simplify a little bit, bring the 1/4 out, and just integrate y, but we have to convert to u's and v's. Y is the square root of v minus u over 2. U went from -4 to 0 and v from 9 to 16. The √2 can come out front. And then we're just integrating v minus u to the 1/2 with respect to u. If I have v minus u to the 1/2, I have to take into account the minus 1. So yes, we will get v minus u to the 3/2 times 2/3, but we get a minus because of the minus in front of the u. We still have dv. We can cancel a 2. We'll rationalize the denominator. That'll give us 4 down below. Multiplied by 3 gives us 12, and we'll also bring the negative out. Evaluating at 0, we have v to the 3 halves. And then putting our -4 in, we have v plus 4 to the 3 halves, dv. Integrating, we have minus root 2 over 12 times the quantity v to the 5 halves times 2/5 minus 2/5 v plus 4 to the 5 halves. And we're evaluating from 9 to 16. We can pull the 2 out, that'll give us a 6, and when we pull the 5 out, we'll have a denominator of 30. So far we have minus root 2 over 30. Remember that when we raise a number to the power of 5 halves, we're raising it to the power of 2 plus a half, which gives us a squared root a. So 16 to the power of 5 halves is 256 root 16. Well, that's 1,024. Minus 20 to the power of 5 halves. Well, that's 20 squared root 20. 20 squared is 400. We can pull a 4 out of that root 20 to give us 800 root 5. Then we subtract, plugging in the 9. Square root of 9 is 3 to the power of 5. 3 squared is 9, squared again is 81, times one more factor of 3 is 243. And then we plug in 9 plus 4, which is 13, to the power of 5 halves. That's 13 squared root 13. 13 squared is 169 root 13. To simplify this further, we'll distribute the negative. We'll have negative 1,024 plus positive 243. That's going to be minus 781. To that we add 800 root 5, and then minus 169 root 13. I want to show you, I think, a remarkable example. Consider the equation for an ellipse. We'll make the following substitutions. In the UV space, the original ellipse is described by u squared plus v squared equals 1. The domain of u's and v's then will be the unit disk, whereas the interior of the ellipse will be the domain for x's and y's. I want to find the area inside of this ellipse. To do so, I integrate just the area element, but the limits of integration are going to be messy. So I'm going to use the Jacobian. We made the change of variables. X equals a times u, y equals b times v. The Jacobian is going to be the absolute value of the determinant of the matrix of partial derivatives, which will be a0, 0b. This gives us ab. That implies then that the original area element dx dy will be ab times the area element du dv. So instead of integrating over x's and y's throughout the entire ellipse, we'll integrate over u's and v's within a unit disk. The integral of r dA, then, will be the integral over the unit disk of ab du dv. The ab can come out of the integral since those are constant. So we're just integrating du dv over the unit disk in uv space. But the area of the unit disk is pi r squared. So it turns out that the area of the ellipse is pi a b. That's a lot easier than what you might have done in the past. Also note that if A and B are equal, then you're not really dealing with an ellipse, you're dealing with a circle, and the common value is equal to the radius. So if A and B are equal to a common radius r, you end up with the formula pi r squared for the area of the disk. As you can see, to find the area of an ellipse, you take pi times the product of the length of the semi-major and the semi-minor axis. That's kind of a neat formula. Let's see if we can extend this to the ellipsoid. In higher dimensions, you still have the absolute value of the determinant of the matrix of partial derivatives, which I'll abbreviate as just this. This is going to be a matrix, an n by n matrix. In addition, the in-volume element will be the Jacobian times the in-volume element in the variable space with respect to the u's. For an ellipsoid, we'll make the substitutions x equals a times u, y equals b times v, z equals c times w, in which case our Jacobian will be the absolute value of the determinant of a00, 0b0, 00c, or abc. It follows that the integral over the ellipsoid of the volume element will be the integral over the unit ball of ABC du dv dw. It follows that we get ABC times the integral over the unit ball of the volume element in UVW space. That's ABC times the volume of the unit ball. But the unit ball has the volume 4/3 pi 1 cubed. So the answer to the volume of the ellipsoid is 4/3 pi ABC. I want to look at another example. Remember, I'm requiring you to memorize the transformation formulas between rectangular and spherical coordinates. X equals rho cosine theta sine phi, y is rho sine theta sine phi, and z equals rho cosine phi. Let's abbreviate these by rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. To calculate the Jacobian, it's dxyz over d rho phi theta, and this is the order in which we take the derivatives. The derivative of x with respect to rho is cosine theta sine phi. Let's do all the derivatives with respect to rho first. Now the derivatives with respect to phi. The derivative of x with respect to phi is going to be rho cosine theta cosine phi, and then we get rho sine theta cosine phi, and then minus rho sine phi. Now we do the derivatives with respect to theta. We'll have minus rho sine theta sine phi, rho cosine theta sine phi, and 0. Now there are some tricks of the trade when it comes to determinants. One is that you can factor out of any row or any column. So for instance, on the middle column, we have a common factor of rho. That can be factored out. Same thing about the last column. The rho can be factored out. The last column also has a factor of sine phi. So we'll still have the minus sine theta and the cosine theta, but the sine phi's are gone. Now, we have here a rho squared sine phi. You'll remember that dx dy dv was rho squared sine phi d rho d phi d theta. If that's true, then the determinant of what is left over had better end up being 1. Let's see if that's true. We'll have rho squared sine phi times. We can calculate the determinant using the special formula. Multiplying down diagonals this way, we'll end up with 0. This times this times this gives us cosine squared theta, cosine squared phi. And then we have this minus sine theta times these two. We'll have minus minus is plus sine squared theta, sine squared phi. And then we subtract products going in the other direction. This times this times this will get a minus sine squared theta, cosine squared phi. And then this times this times this gives us 0. This times this times this gives us a minus, let's see, where was that again? Here, here, and here. We'll have a cosine squared theta, sine squared phi. That better simplify to 1. Let's see if it does. The minus distributes and we get plus on all of those terms. We can combine these terms. They have a common factor of cosine squared phi. What's left is cosine squared theta plus sine squared theta. On the remaining two terms, we have a common factor of sine squared phi, sine squared theta plus cosine squared theta. Using the Pythagorean identity twice, we'll then have rho squared sine phi times cosine squared phi plus sine squared phi. Using the Pythagorean identity again, we have rho squared sine phi. This proves that the volume element in spherical coordinates will be rho squared sine phi d rho d phi d theta.